Steve Shenker here for this colloquium. Steve is the Richard Herschel Weiland Professor of Physics at Stanford. He received his PhD from Cornell, was a postdoc at the University of Chicago, and then the Institute for Theoretical Physics at Santa Barbara, before joining the faculty at the University of Chicago, then finally moving to Rutgers, and then finally Stanford. He has made important contributions to many areas of theoretical physics, including the dynamics of gauge theories and conformal field theories, and his work on non-perturbative formulations of string and M theory. And most recently, he's been at the center of many exciting developments in quantum gravity, connecting black holes, chaos, and quantum information, and other disparate areas. And that's what he'll tell us about today. Go ahead, Steve.
Okay, thanks. Well, this is a hybrid audience, and for those of you that don't know, this colloquium is part of Hiroshi Fest, which is a celebration of Hiroshi Oguri's 60th birthday. And so because of that, I'm going to take a few minutes to say a few words about Hiroshi. I actually can't remember when we met each other first in person.
I remember 87.
87 was that?
Maybe earlier.
Okay. What I remember is the time that I heard about you, which was around that same time, maybe 87, 87 or 88. And it was when I was a faculty member at the University of Chicago. And Yuichiro Nambu, our esteemed colleague, called me into his office. And he wanted to show me a letter of recommendation. And probably for most of you, I need to explain to you that letters of recommendation used to be physical objects. They were typed on pieces of paper, they came in envelopes, and they had these things called stamps on them. And in particular, this letter came from Japan, from Toru Oguchi. And when you sent things across continents, the paper was very flimsy and light because the weight mattered. This was an airmail letter of recommendation. And so there was a flimsy piece of paper, and typed on it was a letter. The text contained a description of your early work on two-dimensional conformal field theory and some very laudatory, evaluative statements. But the real content of the letter was written out in a few lines just below the signature in Japanese, and those Yuichiro Nambu translated for me. And I don't remember the precise words, but the clear sense of them was, this guy is a true singularity. He's the best student I have ever seen in Japan, and you better hire him immediately as a faculty member, even though he's still a graduate student. And Chicago proceeded to do that, as I recall. And well, one thing that hasn't changed about letters of recommendation and transition from paper to bits is what's the polite word? They're often somewhat hyperbolic, I guess is the word. This is a case though where the letter was no more than accurate, and it's clear that Hiroshi has become one of the intellectual leaders of our field, and so I'm happy to be here to celebrate. But there's another part of Hiroshi's career though that I need to underline, as several people have earlier. Well, for my sins, I've spent a significant part of my career doing institutional group building and group maintenance and emergency repair jobs on occasion. And, you know, on occasion, I found it rewarding, but quite often I found it frustrating, aggravating, anxiety-producing, and almost certainly incredibly time-consuming. And now I look at Hiroshi, and you're one of the founders of Kavli IPMU in Japan, and are currently the director of that institution. You're the founding director of the Burke Institute for Theoretical Physics here, and you're chairman of the board of trustees at the Aspen Center for Physics. And I need to stress, this is all at the same time. And in addition, you're doing cutting edge research. And this, well, I frankly don't understand how you do it, but I have to say that, you know, our field owes you a great debt, and I'm personally grateful for all that you've done. It's made a big difference. Well, I guess now I should turn to closer to the colloquium. Now, I took as my task when I was asked to give a colloquium as part of this fest that I should address the colloquium not to the large number of experts that have gathered here to help celebrate, but to the larger part of the physics community. Some of you, I guess, are actually here. And so I have to give a warning to all the experts that are here that there's not going to be much of this colloquium you haven't heard a number of times before. And well, the only thing I can say is, well, I won't be insulted if you discreetly consult your electronic devices. There's another, I guess, another thing I can offer. For those of you that were not part of this birthday, this talk was preceded by this bravura performance by Sachdev-Ye-Kitaev, which, you know, involved scissors, cameras, Mobius strips, magician's assistants, and ended up with things like this. And it was fascinating. And so those of you that want to do your homework left over from that lecture, if you have some nail scissors or something, I of course won't mind that. Well, I guess then with that disclaimer, let me start actually giving a colloquium. Let me stand here so I'm a little closer to you. The subject that I want to talk about starts with black holes. And a key ingredient of black holes is that they're objects with horizons. And these horizons seem to display irreversible dissipative behavior. They have a viscosity, an electrical resistance. And one indication of this is if you ping the black hole somehow and then watch its response. Well, at Caltech, I don't have to explain to you what happens when you do this. This is this famous signal from the first black hole merger event observed on LIGO a number of years ago now, but certainly not forgotten. This, of course, is the theoretical curve, which is the one I'll look at. You can think of this initial coalescence as a kind of initial ping, a perturbation of the black hole. And then at late times, it settles down to a single spherical black hole. And the way it settles down is it oscillates and decays. And in classical gravity, this decay would continue forever, and the thing would reach this nice quiescent, perfectly spherical black hole. But in quantum mechanics, this isn't exactly the way things work. And we think black holes are quantum objects. One Malvicena has called this the central dogma, that we think that black holes, at least when we view them from the outside, as well, at least for some of these black holes we are, they're ordinary quantum systems. And our clearest, deepest understanding of this often goes under the name of gauge gravity duality, the ADS-CFT correspondence, holographic duality. And a little more concretely, there's certain large N quantum systems. The paradigm is a quantum field theory like QCD, where you have N colors of gluons as opposed to 3. And the system, when it's strongly coupled, is dual. That means that there's a dictionary relating it to a rather different system. It's dual to a weakly coupled gravitational system. And the way this is organized is you imagine a space-time. It's anti-de Sitter space-time, and there's a boundary. And this large N quantum system, this gauge theory, I think it's sort of plated on the boundary. These little colored things are gluons. And inside this surface of the sphere is space-time, a bulk space-time. And that's where quantum gravity lives. And part of this dictionary is that if you take a high energy state of this gauge sphere, you heat it up and you get some kind of quark gluon plasma, and you'd make in a collision, an accelerator, that this, under this dictionary, looks like a black hole in the bulk of space-time. Now, in the field theory, there's a boundary version, if you use this dictionary, of pinging the black hole and looking for its response. That is, you compute a correlation function in the gauge theory in a thermal ensemble. Correlation functions in thermal systems, they relax thermally, they thermalize. Okay? And this thermal relaxation is the analog of these quasi-normal modes that describe the ringing and relaxation of a black hole. But now we can try to do a calculation of this using this boundary quantum setup. You insert a complete set of quantum states here, sum over states with a Boltzmann factor, and you get a sum over matrix elements of the operator squared, a Boltzmann factor, and e to the I times energy differences times time, normalized. Now, black holes have all kinds of interesting quantum properties. Hawking and Bekenstein taught us that they have a finite entropy proportional to their area. And if you have a finite entropy, it means the energy levels of a system are discrete. Entropy is related to the density of states. We also expect them to be non-degenerate because of the chaotic nature of black holes. We'll talk about it in a bit. So you can imagine taking a formula like this and asking what happens at long times. Well, at short times, we can ignore this discreteness, it'll relax. But at long times, you just have a sum of oscillating phases. Okay, think about having 10 terms, or I guess, well, let's say 4 terms in this sum. Just a sum of 4 oscillations. It's not decaying, it's just oscillating. And it's oscillating in a kind of erratic way. And it turns out by the time you get there, the signal is exponentially small. So it no longer is doing this nice gravitational relaxation. It starts oscillating. So there's some clash between what you expect quantum mechanically and what classical gravity predicts. Well, we can ask, what is the bulk gravitational explanation for this? And this is sometimes referred to as Maldasena's version of the black hole information problem. Information problems are places where quantum mechanical understanding clashes with what classical or semi-classical gravity teaches us. And this is an example. This is an example well suited to something I didn't explain here, that this black hole, because it's in kind of a container, doesn't ever evaporate. It emits Hawking radiation, but the can kind of bounces the Hawking radiation back into the black hole. So it stays there forever. And so you can monitor this correlation function for a long time and watch it transition from decay to oscillation. Well, the short answer to what is the bulk gravitational explanation for this is we don't know. Okay. And the deep, well, that's not the only problem, but one of the problems is, although we know a precise set of rules for the boundary is a gauge theory, we think we understand what a gauge theory is. We understand it well enough that if we were forced, we could put it on a computer. Okay. We discretize it, put it on a lattice. Now, it might be computationally unfeasible to calculate what you want, but we think we know the rules to set it up. Now, it is an unpleasant truth that even now, well, let's see, a quarter of a century since the advent of gauge gravity duality, many years since the advent of string theory as a theory of quantum gravity, although we know a great deal about the bulk, a lot is kind of an understatement. We don't know all the rules describing it. We know an enormous amount. We know how to compute perturbation theory and all kinds of different limits. We know effects beyond perturbation theory, things you might have heard of, branes, D-branes, NF branes, all kinds of stuff. But we don't have the thing we have in field theory, a complete set of rules that if somebody put a gun to our head, we could put it on a computer and compute. We don't know enough. In particular, we don't know the rules to calculate these discrete energy eigenvalues of a black hole. It's not a question of practicality. We just don't know what equations to solve and what variables. Well, that's irritating. Well, we have some choices. One is you could say, well, this is, this is not a question for now. Let's put it aside. Let's work on something more interesting and more practical. The other tactic, and there might be others, is to turn to a simple model where we can do more. And that's the tack I want to take today, is to talk about how this problem is addressed in a simple model like this. And fortunately, in recent years, a simple model of a black hole in one space and one time dimension, which is a small number of dimensions, has been introduced. It's this famous Sachdev-Ye-Kitaev, which because you're here and because Alexei is here, I suspect you've heard a little bit about. And because this is a model in one space and one time, and this gauge gravity duality relates a system in a certain number of spatial dimensions to a gravitational system in one higher number of spatial dimensions. That's why it's called holographic. the boundary analog of this black hole should be a zero space in one-time system. That means an ordinary quantum mechanical system. And the quantum mechanics is maybe about as simple as you can imagine. You imagine you have n Majorana fermions. Majorana fermion is kind of half of an ordinary fermion. And you take them 4 at a time and you couple them together with essentially random independent couplings you might draw from a Gaussian distribution. So this is just some quantum system that you could certainly put on a computer, and we'll talk more about that. Completely well posed. And although it's not apparent now, the fact that it's not just one quantum mechanical system, for every choice of J's, it's another quantum system. It's an ensemble of quantum systems, and hence an ensemble of quantum gravities. And we'll talk more about the implications of that in a moment. So now we might try to address this correlation function. Well, this is this correlation function recopied. It turns out that these matrix elements they don't do much. They vary smoothly with M and N when you square them. So let's just get rid of them. They make life more difficult. So there's a simpler diagnostic that behaves similarly where you just keep the phases. This is sometimes called the spectral form factor. It's a double sum over energy levels times these phases with a Boltzmann type factor to keep the sum under control. You can see that this double sum is like a product of two partition functions. A partition function with temperature, inverse temperature beta plus IT, and a temperature beta minus IT. So think of this as a product of two partition functions in complex temperature.
Why is there an extra energy in the beta term?
Just because this way it'll keep the sum under control. Okay, you can move one of these correlators around continue it by 180 degrees by half a beta to make it look closer to it. But think about it as something as morally similar, but it's the sum over energies is cut off. So essentially, this is just a Fourier transform of the differences in energy levels with this damping factor to keep things well behaved. Well, now we think we have a simple model black hole. We can ask this question: how does it behave at long time? And because we have this very concrete system, one thing we can do is we can just do a computer experiment. In fact, this is the way a number of us started. We didn't really know what to expect. Being able to do computer experiments in quantum gravity is kind of an unusual feeling for many of us. And it's something that in condensed matter physics and mesoscopic physics is much more familiar. But having this tool, well, it's an important discovery tool. If you don't know what you're doing, at the very least, you can simulate it and see what you think should be going on. All right, so this is the curve that you get. This is time, and this is this spectral form factor quantity. It's a log-log plot. This initial decrease is like the quasi-normal mode relaxation of the black hole. Things damp out. And you can see as a function of time, it doesn't go to zero. It gets pretty small. But then it has a minimum value, it goes up and then kind of levels off. It doesn't look all that erratic, although you can see a little bit of fuzz here, because we've averaged over a number of different versions of this Hamiltonian. We've averaged over J's. I think this is 90 different choices of J averaged over. And we call the features, we had to give them some names to talk about. This is the slope, we called it. This is the ramp, and this is the plateau. All right, the slope is the analog of quasi-normal mode behavior. It doesn't continue forever. It turns into this rather distinctive ramp plateau feature. What does this pattern mean? Well, after puzzling about it for longer than we should have, we realized that it's a signature of something called random matrix statistics. And that's the second part of the title that we'll get to. Now, there's abundant evidence that black holes are quantum chaotic systems. This is something, a big story. It would be another colloquium, but I hope you've heard a little bit about it. The fact that the system relaxes and thermalizes is already an indication of that. It's widely believed, and there's lots of arguments for it, that the energy levels of quantum chaotic systems have a universal statistical property. They obey the same statistics as those of random matrices. So this means if you have some Hamiltonian that somebody hands you of a given quantum chaotic system, you can just replace, for many purposes, that big matrix by a matrix where each of the entries is just a random number you pulled out of some distribution. So it's a much simpler object. And the fact that energy levels of this wide variety of systems obey the same simple property is a remarkable example of universality. Now, I came of age probably in the late 70s and 80s in physics, and at this time, it was kind of the consolidation period of the Wilsonian revolution, the renormalization, where universality was a central feature. And I just didn't know at the time, it wasn't for many years, that there, for a number of years, several decades earlier, there was this enormously powerful other example of universality that was known, that a wide variety of systems have the same quantitatively universal behavior. And in fact, it's actually a little stronger. It's independent of the dimension of the system, the locality of the system. It's only weakly dependent on symmetry. Well, and what is this pattern? Well, there's an explicit formula for the density-density correlation function of energy levels. Here's a piece of a spectrum. This is actually a piece of a spectrum from this SYK model. We diagonalized it in a computer. I think the systems we look at have 60,000 energy levels. Here's a little slice of 50 of them. You can say, given an energy level here, what are the odds that there's an energy level a certain spacing away? And this is a plot of that odds. When the energy levels have no spacing, there's zero probability. The energy levels don't pile up on each other. This is a familiar phenomenon of eigenvalue repulsion that you learned about in quantum mechanics. In a generic Hamiltonian matrix, eigenvalues don't like to be on top of each other. They repel. And then if you go out sort of a certain distance, kind of the nearest neighbor distance in this sort of gas, if you think of these eigenvalues as a gas, there's a little peak. And then there's a trough, and then there's a second peak, kind of where the second nearest neighbor would be. And this pattern decays because this is not a crystal, it's kind of a floppy liquid or gas. And here's a mathematical formula for it that doesn't matter. The slow decay is often called long-range spectral rigidity. This pattern persists for a long time. And the vanishing here is called short-range level repulsion. And this detailed mathematical shape is what is universal in quantum chaotic systems, with a few caveats that I won't go into. And this is remarkable. And so this is the energy spacing. We're Fourier transforming it. The Fourier transform of this curve is this curve. Okay. This sharp transition here gives these wiggles. That's what Fourier transforms do. And the slow decay here corresponds to this linear ramp. So this ramp that we saw in that data is a signature of long-range spectral rigidity. This sharp transition is the signature of short-range level repulsion. And we see that the spectral form factor has this distinctive universal pattern. We're now in a position to ask, what's the gravitational explanation for that pattern, at least in this toy model? All right, so now we have to understand this SYK model a little better. How does it relate to gravity? And there's a long story here, and I'll just try to give you a flavor for it. It turns out, as you can often do in many body systems, you can rewrite the system in terms of collective fields. Maybe an example would be if you have a system of fermions in a metal and you're interested in superconductivity, you might try to rewrite it in terms of the Cooper pairs that form the superconducting condensate. You might introduce a bosonic variable to describe that condensate. Here, the right thing to do is to write a composite variable involving pairs of fermions at different times. And so this is a bosonic field that has two different time arguments. And then schematically, you can write the path integral, if you will, for this fermion quantum mechanics. You can rewrite it in terms of integrals over these collective fields. They're sometimes called Hubbard-Stratanovich fields in condensed matter physics. With some weighting factor, we'll call it an action that depends on these fields. Sigma is a another collective field you need to make this thing work. Don't worry too much about it. This collective action is particularly simple when you average over the J's. Got a simple explicit form. And I want to emphasize that this is an exact rewrite. So anything you can learn here, at least after averaging, you can learn here. And it turns out that these collective fields connect to a gravitational description. So we're sort of inching up to understanding how things might connect to gravity. At low energies, it turns out this collective field description is related to a certain kind of 2D gravity, a theory of two-dimensional geometries, two-dimensional metrics, called Sachdev-Ye-Kitaev gravity. We often call it JT gravity. And concretely, the way it works is imagine you have a two-dimensional geometry. Here it's kind of a disk. This is sort of what a black hole in Euclidean time looks like. If you imagine you have two time arguments, you compute on this geometry a correlation function of a quantum field. And the value of that correlation function is the collective field corresponding to this geometry. So coded in these variables are geometries. So this integral over collective fields is like an integral over geometries with a weighting factor. It's like a proxy for a bulk gravity description. And this is all quantum mechanics, integrating over fluctuations. So it's a proxy for a complete quantum bulk description. So in this simple toy model, and it's really simple and really toy, but we know all the rules. So we can ask this question precisely here. So we should be able to find the behavior of the spectral form factor with these rules. Now, this thing involves two partition functions, two boundary systems. So we need left and right fermions. And so you need a few more collective fields. You need a left-left collective field made of left-left fermions, a right-right collective field made of right-right fermions, and a left-right collective field. And it turns out that the ramp comes from a non-zero saddle point in this integral of collective fields where G left-right is non-zero. It links the left and the right copies. We sometimes call them replicas. These dotted lines are what would reproduce G left-left. These dotted lines are the correlator that would reproduce G right-right. And this dotted line is what would reproduce G left-right. So somehow we need a gravitational object, a geometry that's like a wormhole connecting the left and the right boundary systems. That seems to be part of the explanation for these random matrix statistics from a gravitational point of view. Now, the other part of this curve, this plateau, is substantially more subtle. And I can say, actually, that there's been some recent progress in this problem that just appeared a few days ago by my colleagues that gives, I think, convincing evidence that in many circumstances, you can think of the plateau as coming not just from this topology, but from more complicated topologies where you might add an extra handle onto this, or two handles, plus three handles, and so on. We won't talk about that here, but I'm optimistic now that there is a rather straightforward geometrical description of the plateau as well. This is a slightly more highbrow version of this geometry. We called it the double cone. This is what a two-dimensional black hole looks like. This is the Penrose diagram. These are horizons. You slice out a piece of this geometry and identify things, and you get a wormhole that looks like this. This represents a one-dimensional universe evolving in time. That's why you call it a space-time wormhole. The wormholes that you go to watch sci-fi movies about, these Einstein-Rosen bridges that you might be able to travel to distant parts of the universe on, these correspond to these one-dimensional slices. Now, these wormholes are very interesting. First of all, configurations like this have been found in higher dimensions, which is good because we think that this random matrix statistics is a universal phenomenon that should apply beyond 1+1 dimensions. And so it might be that these wormholes can serve as an explanation for this behavior in more general dimensions. Closely related wormhole configurations have been used to explain a host of other delicate, non-perturbative physics. They actually can be used to explain the long-term behavior of correlation functions themselves. As we heard from Jan de Boer this morning, they can explain things about the eigenstate thermalization hypothesis. This is something having to do with matrix elements and operator product coefficients in highly excited, very massive operators and control field theories. They give an explanation in terms of a gravitational path integral for this famous Page curve calculation of the entropy of evaporating of radiation for evaporating black holes. And more recently, they've given a candidate mechanism for the production of these very strange objects called firewalls that many of us argue about and whether or not black holes contain them in their interior. So these wormholes are useful. They do a lot of good things, but their existence, if they actually exist in the rules, raise a number of puzzling questions. And so in the second part of the talk, especially with the fact that there are some experts around here, I need to agonize with you about these puzzles and talk about them. Michael, nobody has any scissors in the audience. I heard that Takashi, you couldn't bring scissors here because they wouldn't allow them on the airplane. Okay, so is that right? Okay. All right. Well, I'm not sure why I'm worried about the existence of weapons in the audience. I'll go on from there. Well, the blunt truth is that standard gauge gravity dual systems, like the ones that we learned about, where you have a gauge theory like Super-Yang-Mills theory on the boundary, and in the bulk you have anti-de Sitter space in 5 space-time dimensions. We don't average over them. We have one rather unique, very beautiful boundary Hamiltonian. We don't know the rules in the bulk here. Okay, so we're again at sea. We don't actually know how to translate the story directly. But we can try to talk about a toy model when you don't average. We can just take our wonderful SYK model where we have lots of different Hamiltonians and say, nope, you can't average over all these J's. You get to just use one. Okay, well, this actually, in the computer, this is easier. We don't have to run the computer as long. Okay. So we can ask, what happens if we take the SYK model with one choice of J's? Well, then the signal looks kind of different. This blue line is the signal I showed you before, averaging over, I guess, 90. The red line is if you just have just one. These signals look rather different. When you have just one system, this ramp and plateau are noisy. Okay? This noise reflects something about the particular discrete energy eigenvalues that you have in the spectrum of just one quantum system. Now, this is a log-log plot, and so the fact that this noise is constant width means that the noise is of order the signal. This is exactly what you'd expect from random matrix universality. If you pull one random matrix out of an ensemble and compute its spectral form factor, it'll look just like this. And so random matrix universality gives us very strong reasons to believe this red curve is what you'd expect if you could do this calculation in Super-Yang-Mills theory. It would look like this. The second point is, whoops. There we go. Is that even though this is a pretty noisy signal, this is a very long time. This is, again, a log-log plot. The autocorrelation time of this noise is very short. And so if you average over bins, you can see that the envelope of this noise will look very much like the wormhole and plateau signal. And so somehow hidden in this noise seems to be something that could be explained by a wormhole. But it's clearly not enough. There's something else going on. So at the very least, the bulk must contain something else to account for the noise. There's an additional rather qualitative puzzle that arises if you don't average over an ensemble. It's called the factorization puzzle. Sorry. From the boundary point of view, if you have a system, a partition function with two boundaries, left and right, these are just two decoupled Hamiltonians. And you know in statistical mechanics, the partition function of two decoupled Hamiltonians is the product of the two partition functions. Z left right is exactly equal to Z left times Z right. We say that Z left right factorizes. But from the bulk point of view, Z left right contains a left right wormhole. But Z left or Z right on their own, they don't contain any wormholes. There's no place for a wormhole to go. So superficially, at least, Z left right does not factorize. So these wormholes seem to imply a failure of factorization, and that's a puzzle. It's this puzzle. Well, if wormholes are actually there in the bulk, I guess I left a word, then the bulk must contain something else to restore factorization. Well, it seems very plausible that this something else is also the source of the noise. And we'll see an example of that. Now, if we average over an ensemble of Hamiltonians, if we go back to our comfortable stamping grounds, then Z left right averaged doesn't have to be equal to the average of the products. Averaging doesn't respect the product. And so it's natural if you average with the same couplings left and right that you can produce some kind of connection between them. And in fact, this connection between wormholes and fluctuating couplings was pointed out long ago, in work in the 80s by Coleman and Giddings-Stein. But we don't want to average in our real theory of quantum gravity in our world or in the quote unquote ADS world, where we try to explain. So what's going on? Well, how do we study this? And again, we don't know the rules. Okay, so if we try to do this in Super 8 mils, we're out of luck, at least with current technology. But again, we can try to study it in a toy model. So let's examine the collective field description of SYK with fixed couplings. Don't average over the J's. We're free to do this. We can rewrite the fermions in terms of collective fields and don't average. Okay, then you get an expression like this, except this collective field action depends on which J you have in a rather complicated way. Okay. So, but nonetheless, this is an exact rewrite. So it should factorize, it should have noise, it should do all of that stuff. How does it do it? This is, again, a completely well-posed path integral. Well, unfortunately, the bad news is this problem was actually too hard for us to analyze precisely. So what we had to do is we had to make a further retreat. And we've gone from quantum gravity in the real world to quantum gravity in ADS space to quantum gravity in 1+1 dimensions. Now what we have to do is we have to butcher time, and we take the SYK model with just one time point. Okay. Instead of having fermion fields as a function of time, we just have a fermion field. That means an ordinary Grassmann variable. So we're thinking of an integral over n Grassmann variables. That's, morally speaking, an ordinary integral. Okay. That we were able to study. Okay. And from the way that worked, we were able to, I think, produce a plausible conjecture for the way the full SYK model works. So we analyzed this toy model of a toy model rather precisely. And this is what seemed to be the outcome. With fixed couplings, there's another saddle point of the collective fields. The wormhole saddle point stays around, but there's another saddle point. This saddle point has G left left and G right right with the same values that a wormhole would have, but no G left right. So we called it a half wormhole. Well, we called it a half wormhole. Let me leave it at that. And so the idea is this thing without averaging, I should probably have written this as Z left right, is the wormhole saddle point with G left right not equal to 0, plus these two half wormholes. And I'll explain that red line in a minute, where G left right is equal to 0. G left left has the same correlator that it would here. G right right has the same correlator it would here. Now, the contribution of this wormhole saddle is essentially independent of the choice of J. But the half wormhole contribution is very sensitive. And in fact, it's the source of the noise. Okay. And on averaging over the J's, or over a time window, this half wormhole contribution averages to 0. And you're left with a wormhole signal. So places where you think you should have a wormhole that stays around, in the places where something else needs to be there, these half wormholes appear. Now, this has been studied in the gravitational analog in JT gravity by these people. And there you can sort of build a picture for what this funny red line is. It's some kind of boundary condition where the wormhole ends on some sort of break. So there, was another reason that calling it a half wormhole was not completely unpleasant. Well, then we can ask about factorization. Well, it turns out there are multiple possible collective field descriptions. That means bulk descriptions. And with fixed J's, there's no clear preference between them. I told you if you have left and right systems, you better introduce G left right. You don't really have to. You can just integrate out G left right. Collective fields, if you integrate them out, they just go away. Okay. And so then you're left with just G left left and G right right. That presentation manifestly factorized. Okay. So there would be no mystery in that gravitational description for why you could factorize. So this leaves a bulk description without wormholes. In some sense, you've integrated out over all the wormhole geometry. So in this description, G left right manifestly factorized. That's what this description would look like. You have two half wormholes, manifestly factorizes. And because it's just doing the integral in a different way, I could also do the integral by not integrating G left right first, but looking for saddle points. Then you'd find this saddle point plus this half wormhole saddle point, but the action of it is different because G left right is present. That's what this little red line means. So the wormhole and this linked half wormhole contribution add up to restore factorization. So again, these half wormholes, they create the noise and they restore factorization. So in this toy model, this is the way that these puzzles are resolved. Wormholes are present. You can use them when they're useful, but you don't need to have them. And there are ways of curing the puzzles. This is kind of even more appealing. I didn't really write a slide about that. I'll take a couple of minutes to say, suppose you're interested in some of these other applications of wormholes, computing the page curve. A toy example of this is you imagine actually coupling these left and right systems. You have two quantum Hamiltonians, just connect them by a wire. So I'm coupling the coupled psi left to psi right. Then you can go through this whole collective field machine, and then what you find is that, again, you have a wormhole saddle. There's no factorization puzzle there because the systems are linked. But you also find half wormhole saddle. But the wormhole saddle exponentially dominates over the half wormhole saddle. So the noise is a really tiny effect. This is what we think happens in the page curve analysis. There are wormholes that effectively explain the page curve, and there is noise, but the noise is exponentially damped compared to the signal. It's both a feature and kind of an irritating bug of the spectral form factor that the noise and the wormhole signal are of the same magnitude. And this sort of forces us to confront them to get anything like an accurate noise. Well, maybe I'll just conclude then with some questions that have arisen. The big question is, do these structures, wormholes, half wormholes, and so on, do they have parallels in higher dimension? Let me not call them realistic. Let me call them less toy-like models of quantum gravity, like standard ADS-CFT pairs. Well, again, we don't really know because we don't know the rules. Now, the idea of multiple bulk descriptions, that you can have wormholes present if you want, but there might be a way of treating the description differently and getting rid of them. These things kind of echo some ideas that have emerged in other simple model gravitational descriptions. None of these, though, is at least completely satisfying to me. And part of the reason is that we haven't yet made contact with the bulk degrees of freedom that we think are important in this kind of system. String, grains, and so on. And these must have something to do with the way the system operates. Maybe must is too strong, but it seems likely that they should. There's been a program from a completely other direction trying to understand these discrete energy levels and using grains and strings and so on. It's called the fuzzball program. Matur is one of the main champions of it. And it would be nice to connect these ideas to what's going on here. Now, the challenge is that in order to connect with these ideas, you need to deal with these strings and brains in a regime where they interact strongly in a chaotic way. And that's very hard. So what we really need, or what I would really want, maybe, is we need another simple, tractable model in the spirit of this wonderful SYK model to help us to move closer to understanding these rules and really what they are, the rules of quantum gravity. Well, this is my wish list, but it's not my party. So I shouldn't go on at any more length about that. So let me just end by wishing Veruti a happy birthday. Thanks very much.
Okay, we have plenty of time for questions. Any questions? Yes.
Maybe we should start. I don't mean to disrespect you. Maybe we should start with people that are not experts. and then we can get into the weeds. Yeah, go ahead, please.
Back at the beginning.
Yeah.
How did you know that the gravity of the black hole was weakly coupled?
How did I know? You mean from the boundary, from the?
Yeah.
That's where large N comes in. It turns out that the coupling of gravity, G Newton, is related to 1 over N or 1 over N squared. So that was the role of large N. Any other questions from the general audience? Do you count as the general audience? I don't know. All right.
So you mentioned parallel between chaotic behavior and the wormhole.
Yes.
That also, and you mentioned that in high-dimensional systems, we know the wormhole saddle. So other examples where chaotic behavior has been identified also on the CFT wormhole.
You mean using some direct CFT analysis?
Where this would fit in the full picture.
I think the short answer is no. I don't know of a direct analysis using CFT type tools. Again, it's these are very complicated. Some of the statistical things, probably the closest is the kind of calculations that Jan de Boer explained this morning, where you try to derive bulk geometries that might explain some of the statistics of CFT data. Let's say operator product coefficients, but a direct derivation, let's say, of the noisy numbers in the CFT, I don't know, and it's, well, almost by definition, it will be very difficult. Okay, so I guess we're into the weeds.
Yeah.
You're up, Daniel.
Actually, it's a question.
No, it's okay. I wasn't trying. I probably was trying to avoid answering. But, yeah, good, please.
Is there a slogan for why, when you sum over J, the half wormhole goes away, but the wormhole doesn't go away?
A slogan.
Yeah, is there a way to explain that with just saying I do the calculation?
That's a good question. I believe there is, but it's not. I'm blocking on it. But I think yes. I don't think it's necessary to just do the calculation. Yeah. Well. Yeah, but I'm trying to think of the way. I mean, technically, and this may be just a calculation. We compute the variance, and then you can study as a function of the collective fields how big the variance is. Okay, and there's a self-averaging region and a non-self-averaging region, and you can see where each saddle point lives. But that might not be much better than what you call a calculation. Okay, so but in terms of an obvious conceptual answer, I'm blocking that, but I suspect there is.
So are you waiting to
speculate what's going to happen in higher dimension?
Yeah, I'll speculate.
Yes.
Um,
Can you expand?
Yeah, I think, well, what I would hope would be that there would be this analog of multiple bulk description. That there would be, there would be some presentation where gravitational variables would be useful. And there would be things like connected wormhole geometries. And for certain applications, time average of the spectral form factor, linking left and right, they would turn out to be saddle points in some description. But then there would be other quantities where you would need, it would be a better thing to do to integrate over. Like if you wanted to prove factorization, introducing G left right is not a good idea.
So if you fix the boundary theory with fixed coupling,
Yes,
there must be a way of restoring factorization.
yes.
Would that make the mechanism you pointed out in two-dimensional universal in higher?
Oh, no, you mean like these detailed half wormholes? No, I have no strong confidence in that at all. That I
So that can be special in two-dimensional. In high dimensions, there can be other ways.
I would guess so, although I don't know. I think the main lesson is that there is room for other kind of non-geometrical objects to appear. And then it's not, and I think the most important thing is it's not necessary, once you say, oh, there's non-geometrical things, fuzzballs or something like that, then you have to abandon geometry. That's not clear to me. It's possible for them both to coexist. I think that would be my hope. Okay. And I think you might have a choice. I think there probably is a description where everything is non-geometrical, but it's not too useful. It'd be nice to have black holes and stuff. Yes.
There's an online question. Go ahead.
Could you maybe say briefly what role wormholes play in the firewall paradox that you mentioned briefly, and in particular what the ramifications for having these multiple bulk descriptions are for that?
Yeah, let me see if I. So this is not my work. This is the work of Douglas Stanford and Zhenbin Yang. The multiple bulk description, I don't have anything to say. Let me see if I can try to give a flavor for their argument. So you imagine the eternal black hole geometry. You know that the length of the Einstein-Rosen bridge increases in time. It turns out, as actually Phil Saad first showed, that one effect of a geometry like that emitting a baby universe, that is, a wormhole, if you time slice it, can look like a baby universe, is to make the Einstein-Rosen bridge shorter. And the new observation of Douglas and Zhenbin is that, in fact, this can be very dramatic. There is a finite probability for the Einstein-Rosen bridge to shorten so much that it doesn't go to sort of its minimum time zero value, to go back to negative time. Okay. So in some sense, you're tunneling. That's what these things are. They're instantons. From an ordinary late-time black hole to a white hole. And it turns out if you perturb a white hole with a quantum, it acts very much like a shock. It acts like a shock wave that an infalling observer will experience as something like a firewall. That's kind of the flavor of the argument.
We have a question from one of the online attendees. Given that J is random in SYK, how is the ensemble of gravity to be interpreted? In other words, what would each sample represent in the corresponding gravity system?
Yeah, good question. I presume I think the limited answer we have is it would correspond to a different weighting of these half wormholes. You would have black holes, wormholes, which would be gravitational and wouldn't depend much on which J you have. And then you'd have these other, if you will, half geometrical features, these wormholes with half wormholes with a boundary condition. I don't know why I'm talking to the laptop. That these half wormholes would be, their weight would be sensitively dependent on which particular J you have. And that's where the data of each individual Hamiltonian would be stored.
Since you had on your slide the question of a simple model
Yeah,
similar to SYK, I think you know what I'm gonna say.
yeah.
What about the tensor model? Do you have any?
I just don't, I don't know how to work with them. I mean, I don't know the bulk description of them very well. Like what,
They the large and limits are similar.
Yeah, but
and they're not random.
unfortunately, these kinds of things are not in the large, these are non-perturbative in N. So you need to control, you need finite N collective field control. And I don't know how to do that in the tensor models.
We don't have any speculation what happens there.
I would guess that the spectral form factor curve will look like that red line. That's a cheap speculation. Random matrix universality is a very powerful thing. So I would guess that it would need to have some of the features we're talking about. But what I don't have is the analog of this complete bulk description. This is what this toy, this toy model has this very powerful thing. There's just an integral, a path integral that has everything in it. And so you can go poke around in the nooks and crannies and find out where all this weird stuff is hidden. And I don't know how to do that in the tensor model.
I think, Jake, you had a question, sir?
Yeah, so you talked about these multiple descriptions, right?
Yeah.
It's one description where you have the wormhole, like the link half-wormhole.
Yes, yes.
Others where you just have the half-wormhole.
Yes.
And you don't have the wormhole.
Yes.
And then it's kind of analogous to sort of the choice of gauge fixing. You can view it maybe as a gauge fixing. And in normal gauge fixing of a gauge theory, there's sort of two things you can do. One is you can gauge fix, then you can path circle over gauge fix variables. The other thing is you can do is you can sum over everything, and then you can quotient by gauge of n.
Yes.
You on the lattice. So is there a version of the bulk? Do you believe there's a version of the bulk where you don't gauge fix first, or is it really fundamentally that there's no description that covers everything?
I don't know the answer to that. I don't know the answer to that. I'd like to understand, and Nadi has taught me a little bit about how this very lowbrow collective field thing can be interpreted as a kind of gauge symmetry. That would be the place I would start, because this thing is concrete enough that, it's an integral. We should be able to, make some statement like that. But I don't have a sharp answer. But I think it's something that one could try to explore.
Yeah, I think just time for one more question. Go ahead.
So okay, you mentioned we understand the ramp coming from the wormhole, and based on the new work of Stanford and company, we understand the plateaus and the entire genus. What is the sharp transition function? Why is there short range level revulsion?
Right. So the trick in explaining things as a sum over geometries is you smooth out that sharp corner. The quantity that is calculable by summing over higher topologies is a smoothed out version of the ramp. So I actually have the misleading slide up here. If you look at the numerics, this isn't so sharp. That's because you've actually smeared out over different energy windows. You've worked at finite temperature, not finite energy, not a fixed energy. And what happens is that smooths out this sharp corner. And this curve, they argue, well, they conjecture, and I think there's a lot of plausibility arguments that this is true. Well, it's actually, they have enormous evidence it's true. That curve is actually described by a convergent expansion. Okay, and so this smooth curve you can describe as a sum over different topologies.
Okay, and it's dominated by the single wormhole.
That's right. At short times, it's dominated by that, and then it starts smoothly curving over. Okay, and so that's so it's maybe morally speaking, it's like taking a Borel transform. You turn this non-perturbative effect into a perturbative effect you can compute by a power scheme.
I would agree with the idea that they're doubly non-perturbative.
Well, because sometimes you can evaluate non-perturbative effects in a convergent series, let's say by taking a Borel transform. And so this is kind of a transform of this original quantity where things are just doubly non-perturbative into something that has a convergent series. And then you can compute that convergent series geometrically. And so, of course, that's much more appealing. The main thing that's appealing about it is it's something you might expect to generalize to higher dimensions, in a more straightforward way.
Okay, thank you so much for all the questions. Let's thank Steve again.